Hello everyone, my name is Dmitry, and today I wanted to present my presentation, my research, and to join with my supervisor, Bach, and it's called Slice Cross Regression with Score Function. So our goal is to consider nonlinear regression, and we consider projection dispute model. We use it because we cannot solve nonlinear regression without any assumptions due to Gaussian dimensionality. So y is some function g of projections multiplied by x plus some nodes. And our goal is to find this dimension reduction, which is often called EDR subspace. Okay, what approach we use? There is some trick we can use. It's called Stein's lemma, and it provides us with expectation of score function of x multiplied by y is in our space, where score function defined as follows. It is negative gradient of logarithm of probability density. And also we extend this Stein's lemma and we use slicing, like slice cross regression did, and we show that expectation of score function with given y also in our EDR subspace. So we have several results. First of all, we developed two methods, CADA, which means sliced average derivative estimator. And also we have a method which called SPHD, slice principal Hessian direction, which use second score function algorithm. Also we have a lot of mathematical analysis of this estimator, and we proved rate of consistency. It is actually a root n consistency with some given assumption, mild assumption. And also, in practice, we don't know score function. That's why we need to learn it as well, and we did it in two ways. One is very simple, and the second one uses some regularization term. And here some graphs. The first one shows comparison of method with a non-score, and the second one shows results with a non-score. So the x is x, it is the size of sample, and x is y is error between estimated and real subspaces. Thank you for your attention. You can ask me more questions as opposed to.
We have a poster with my student Sarah Nair and my colleague and my collaborator Yonina Eldar on non-convex phase retrieval of low-rank matrix columns. Essentially, this extends the recent area of work on single vector phase retrieval to the problem of recovering a low-rank matrix where you have phaseless measurements of each column of the matrix. Applications, phaseless measurements occur everywhere, including a lot of new applications in distinography. So in this poster, I'm giving you a top-level version here, details are in the poster. We develop an algorithm that we call ultimate trunk that exploits the low-rank structure of X both for the initialization step, where we borrow the truncation idea from the truncated vertical flow paper. And the rest of the algorithm is an intuitive modification of the Gershberg-Saxton algorithm, or more commonly known as the ultimate phase algorithm, since I guess that's more popular these days. We obtain high probability sample complexity bounds for the initialization step in this poster. And then, of course, what we show is when the rank of X is low enough, then we can recover each column of X with less than n measurements, much less than n measurements, as we will talk about. So here's the problem setting. You have a matrix X with columns x1 through x3. So for each vector xk, you get m measurements of this form, EIK transpose xk whole square. And the key here is that you have a different set of, or you have an independent set of measurements for each vector xk. And that's the key point that's needed to show that you need to show or even to demonstrate that you need fewer measurements for exact recovery of this matrix because you're exploiting its low rank structure. And that's pretty much it for me.
So good afternoon, everyone. So this is a joint work with Hoi-To and Moulines, who's my PhD advisor. So essentially in our work we look at the Frank-Wolfe algorithm. So we want to minimize the function of our convex bounded set using the Frank-Wolfe algorithm. But we consider non-convex objective, which may vary with time, and also we assume that we don't observe directly the gradients, but we can observe it with some maps. So quickly to say what we do. So for the measure of stationarity, we follow the work of Simon and Julien, and so we define GT, which is a Frank-Wolfe gap, to measure the stationarity. So it has a nice property of being affine invariant. And so our results, so we look at the Frank-Wolfe algorithm, so the vanilla Frank-Wolfe algorithm with the step size which is of the form 1 over t as a bar alpha. And so we look at the stationarity, and essentially what we are able to show is that we get 1 over square root of t convergence rate. We also can get a fast convergence rate under certain conditions. And the sequence of iterates admit some limit points and stationary points. And we apply that to online learning and distributed learning. So please come as a poster if you have more questions. Thank you.
Hello, I'm Gora. I'm a scientist from the University of Warsaw, and my poster presents research on approximating traffic simulation using neural networks, which is a joint work with my colleague, Karol Kurach. So the ultimate goal of this research is a large-scale traffic optimization, so making traffic in large cities such as Warsaw or Barcelona as smooth and efficient as possible. So this is very practical application of neural networks and optimization methods. And for this task, I'm developing software for large-scale traffic simulation, which is called Traffic Simulation Framework. You can see a screencast of a user interface of this software. And I'm applying this tool to analyze network structure or evaluate quality of traffic signal settings for a traffic signal setting problem, which is non-convex and was proved to be NP hard for very simple traffic models. But as you may expect, the problem is that running such large-scale simulations is time-consuming, and usually for many traffic optimization tasks, we need to run large numbers of simulations. So how to do it efficiently? Our idea is to approximate outcomes of such simulations using neural networks, and for this task, we developed a TensorFlow-based tool, which is called TensorTraffic. And we trained neural networks to approximate outcomes of traffic simulations. And the initial results are very promising. We tested different configurations of layers and number of networks and learning rates. And average relative error of our approximations are acceptable, which may make real-time traffic management possible, and it may be especially useful in the era of connected and self-driving cars, in which the traffic must be quite good, predictable. So if you are interested, try to chat and see my poster. Thank you.
paradigm. This is a joint work with my colleagues Soham, Mário, Chris, and Tom. Here I present an empirical study of ADMM for some non-convex problems. If you do not know ADMM, it's a specific form of triangle view method. Basically, we will solve this form of objective. It's the sum of two functions with respect to a linear constraint. And the ADMM steps is like the following three steps. It basically solves the Lagrange of this objective with a quadratic penalty for the constraint. You will solve the two sub-problems alternatively and with a dual instance. Basically, it's generally often used for non-smooth functions because when you add this quadratic penalty, it's easier to solve for those for non-smooth terms. You will often use the proximal operator for this. And in this ADMM method, there's only one free parameter, tau, and we will study about this parameter. This is an empirical study, so we make no assumptions of functions h and t. Generally, if they are convex, the theory is well studied, and we do have some theory for non-convex case, but it's quite strict, requires some like KRD equality and smooth and the rank on the linear constraints. So we propose to study those questions for non-convex problems. Does it ADMM converge in practice, and does update order matters, and is a local minimum good, and is a penalty parameter good, is a penalty parameter matter. And we consider those applications for like L0 non-regularizers. It's quite popular to use ADMM to solve those problems. And for phase retrieval, ADMM is one of the solvers. For eigenvector problem, I don't think anybody will use ADMM to solve it, but it's still interesting to study it. It's a quite easy form of manifold learning and manifold constraint learning. And we present some empirical studies. More results can be found as a poster. And basically, we will start. We found that the method, the penalty parameter, is very important for both convergence speed and the quality of your solution. And some recent adaptive ADMM method seems to be working quite well for those problems. And if you want to know more, please come to our poster. Thank you.
Hello everyone, my name is Zheng. I'm from Syracuse University. This work is joined down with my advisor, Liang, and the professor I teach from Ohio State University. So we consider the original phase retrieval problem. You want to recover a vector x, which is in n-dimensional space, just from the magnitude of its linear measurements. Which is yi equals the inner product of ai with x and take the absolute value. Previously, in 2014, Emmanuel Candice proposed a Wortinger float, which minimizes our non-convex loss, which is written at the left-hand side. And it showed this by minimizing this loss function, it returns the exact recovery with fast convergence guarantee. What we have done is we modified the loss function to be non-smooth but also non-convex by dropping the square in the parentheses. So surprisingly, this modification gives us advantage to have the gradient descent converge faster. We can get a hint from these two graphs. The right one is our loss function, the loss surface. The left one is the Wortinger flow loss surface. You can see our loss surface behaves more like a quadratic function locally, so this which is known to be easily minimized in practice. And moreover, we consider the stochastic version of RWF, and we just for each step we just choose one sample randomly, doing the gradient update, and surprisingly, it converts very fast in practice, and we also proved that it converts linearly to the global minimum, and if we can initialize it by spectral method. Moreover, we show that the Cosmos method can be viewed as a special case of this IRWF, and by making this connection, we show the linear convergence of Cosmos method, which has not been done in previous literatures. As a future direction, I'm very interested in understanding how does the stochastic method escape local minimum when initialized randomly, because it is well known that the phase retrieval problem does not have bad local minimum if the sample size is very large. However, in the regime with only moderate number of samples, indeed there exists a bad local minimum, and in this case, the stochastic method still successfully recovered. However, the gradient descent often fails. Thank you.
Hi everyone, I'm Murthy. I'm going to talk to you today about LSR1, second order optimization method for deep learning that I developed with my colleague Nigel Duffy at Sentient Technologies. So the primary motivation for this new approach was to have the ability to use as large mini-batch sizes as possible during the course of neural network training because we wanted to make as few parameter updates as possible due to certain bandwidth constraints. So second order methods, in particular quasi-Newton methods, were attractive to us for a couple of reasons at least. One was that due to their use of curvature information, they could get to an optimal solution in fewer steps. And secondly, using a large mini-batch size with a quasi-Newton method could give us lower variance estimates of the curvature matrices using the gradient estimates. LBFGS is probably the most popular quasi-Newton method that's used in machine learning. But in the literature, at least 3 critical weaknesses have been identified with respect to its application. There is a proliferation of saddle points in the objective function, which due to the positive definite Hessian approximation used by LBFGS causes it to get stuck. There's a problem with ill conditioning of the curvature matrices, and there's the issue that LBFGS uses a line search which involves multiple gradient and function evaluations. So we tried to devise a solution to address these 3 issues, and what we came up with was basically a limited memory symmetric rank 1 update. Symmetric rank 1 update is one of the lesser known quasi-Newton methods, whose interesting property is that it uses an indefinite Hessian approximation, which gives it the possibility of being able to go downhill at a certain point. We can also use a trust region method instead of a line search to make parameter updates, which helps us avoid a line search. And our hypothesis was that we could improve conditioning of the curvature matrices using batch normalization, and this is something we tested empirically. So to summarize our preliminary experimental results, what we found was that LSR1 performed competitively with several other first order methods and LBFGS with or without batch normalization. It performed much better than LBFGS with or without forgetting, and batch normalization appeared to improve the early performance of LSR1 in particular, And so that seems to be a promising direction for future investigation. And I'm happy to chat more about this at the poster. Thank you.
Okay, thanks a lot for all the poster spotlight presenters. This was the last talk session of the day. Now we'll have another poster session, so I encourage everyone to come to the posters. And before that, I would like to thank all the speakers and all the poster presenters for their submissions and their contributions, and all of you for your attention.